Vin Future Prize, a new global science and technology prize for humanity from Vietnam. One Vin Future grand prize of $3 million. 3 additional special Vin Future prizes valued at $500,000 each. Vin Future Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Good morning, good afternoon, good evening, ladies and gentlemen. Welcome back. We are on the 5th episode of the Vin Future Innovatalk series. And today we are going to talk about science, about technology, and also about innovations around the world. Relating to the topic of today, I will reveal after a minute. I'm Min Chiang, and I'm the Communications and Marketing Senior Manager of the Vin Future Foundation. Today, it's my honor to talk to you as the moderator of today's webinar. And today's webinar will take us on a journey of discovering and developing the highly efficient solar cells. Ladies and gentlemen, and our beloved scientists, solving global warming issues and in mitigating our impacts on the environment have always been urgent. And I believe that all of us have been familiar with renewable energy in general and solar energy in specific, and in energy resource that has been popularized and widely used in the past years. And in today's session, we are going to explore the novel material and a new generation solar cell. We call it Metal-Halide Perovskite, with remarkable power conversion efficiency, with the chance for us to require lower investment and also easy fabrication. And we are very delighted to have the participation of the world's leading scientists in this field because of their talents, hard work, and also significant contribution to science. Let us welcome the chair of today's webinar. Please welcome Professor Sir Richard Henry Friend, FRS, Director of the Winton Program for the Physics of Sustainability and of the Maxwell Center, University of Cambridge. And also, let us welcome distinguished guest, distinguished speaker of today's webinar, Professor Henry Snaith, FRS, Professor of Physics, Bing's Professor of Renewable Energy, Group Leader of Photovoltaics and Optoelectronics Device Group, Department of Physics, University of Oxford. Thank you so much, professors, for for being today with us and for your sharing in the upcoming parts of today's webinar. And before our chair, Professor Richard Henry Friend, will share a few words to you about the topic of today's webinar, I would love to introduce to you the topic video where we will look at some of the images and to get some of the information about what we are going to talk about today. Please, video.
Have you ever imagined what are humans doing to our planet just by producing and consuming energy? Population growth and economical development are driving greater energy consumption around the world. Energy consumption contributes to pollution, environmental deterioration, global greenhouse emissions, and affects human health. That's when we talk about renewable energy. The use of renewable energy derived from natural resources such as sunlight, wind, rain, tides, waves, biomass, and thermal energy stored in the Earth's crust is on the rise. It generates energy that produces no greenhouse gas emissions and reduces some types of air pollution, diversifies the energy supply, creates economic development, and jobs in manufacturing and installation. Among all, solar energy has always been considered as one of the most abundant sources of energy. In 2021, IEA reports show that power generation from solar photovoltaic increased by a record 179 terawatts per hour, marking 22% growth in 2020. As of 2021, solar photovoltaic accounted for 3.6% of global electricity generation, and it remains the third largest renewable electricity technology behind hydropower and wind. Joining this month's webinar, You will have the opportunity to listen to the story behind the discoveries of perovskite solar cells, a promising material to bring photovoltaics field to the next level. Having started a new field of research gaining both academic and industrial following, perovskite solar cells could be the future of energy. The chair of the webinar is Professor Sir Richard Henry Friend, a member of the VinFuture Prize Council, Director of the Winton Program for the Physics of Sustainability of the Maxwell Center. He is the owner of the 2010 Millennium Technology Prize. His current research interests are directed to novel schemes that seek to improve the performance and cost of solar cells.
It is beyond doubt that the future of energy is electric. Solar, wind presents new opportunities.
Our distinguished speaker, Professor Henry Snaith FRS, Professor of Physics, Binks Professor of Renewable Energy, Group Leader of Photovoltaics and Optoelectrics Device Group, Department of Physics, University of Oxford, will share with us about the discovery and development of perovskites in efficient solar cells.
We discovered these perovskite materials that produce power at a much higher efficiency than any other material we'd looked at. When we started looking at this material, it was delivering over 10% efficiency, which was already competitive with some commercial PV products. That's risen up to over 25% efficiency just as a single absorber layer. We can actually combine it with silicon by making a so-called tandem device. And if you could make an infinite number of junctions, you could get up to around 83% efficiency. The prospect for long-term advancement of getting close to 100% efficiency is actually feasible.
The upcoming VinFuture Innovatalk will take place on October 20th, 2022 at 3:30 p.m. Vietnam time, UTC+7, which corresponds to October 20th, 2022 at 9:30 a.m. UK time.
We really want to talk to Professor Sir Richard Henry Friend right now. Hello, our friend. How are you?
Good afternoon. It's a pleasure to be on this lecture. I'm very pleased to be chairing this session. First, I'm very pleased to introduce a very good friend, Professor Henry Snaith, who, as we've just heard, is a professor of physics at the University of Oxford. He has led one of the most surprising advances in semiconductors in the past several decades. A very surprising discovery in his lab in, I think, about 2011, that reveals that there are families of materials that no one suspected would work well as semiconductors and to make solar cells. These are the perovskite structure materials that he'll talk about further. What is so surprising and so important is that in the field of semiconductors, we have become accustomed to silicon being the one semiconductor that really works and everything else being not good enough or too expensive. And the way we look at the prospects for other semiconductors has been conditioned by our presumption that it is always going to be silicon. Silicon does a great job for solar cells. We have borrowed like the technology that produces microprocessors and use that to make very good solar cells. But silicon is not the sole answer. And as Henry Snaith will tell us more, if we can find other materials where we can tune color and find cheaper ways to manufacture, we really can open up the possibilities to make solar cells more affordable, better performing, and make an even larger contribution to renewable energy. So it's a remarkable story, and it's remarkable not just because of its potential impact on meeting global carbon dioxide reduction targets, but also behind the performance that these perovskites show, there are some extraordinary discoveries about how semiconductors work differently to silicon. It's as though we are going to have to rewrite the textbooks for how semiconductors work, because these perovskites have just produced many, many surprises that came very unexpectedly. So that parallel scientific and industrial trajectory produces a remarkable story, which we're going to hear about. I'm really delighted that it is Henry Snaith who is going to give this talk, because it is his group and his discovery that has set the world going, both on the science and on the route towards getting to large markets. So it's a real pleasure for me to introduce Henry Snaith to talk about the discovery and advances in perovskite semiconductors for solar cells.
Well, thank you very much, Richard, for a very gracious introduction, and thank you very much to the VinFuture Prize for asking me here to share some of our discoveries and the work we've been doing, and also for having put together actually a very impressive introductory video. I can only hope that my presentation lives up to some of the expectations now, but I will share with you in the following 15 minutes some of the work we've been doing and try to put it into a little bit of context as well. So if you bear with me, I think this is the time that I should share my screen and start the presentation. So here we go. So as has been mentioned, I'm going to talk about metal-halide perovskites and their journey from discovery to highly efficient and stable photovoltaic technology. I should just start, it's been mentioned, but silicon has done a remarkable job of producing efficient and scalable solar cells. When I started working in photovoltaics, which was more than 20 years ago, the premise then was that silicon was never going to be cheap enough. But it has become cheap enough. It's become cheap enough through industrial scaling and through a lot of advancement. But the opportunity now for new materials is to do something better. We've realized that efficiency is absolutely critical. And this is really where new materials can play a role. They can play a role in trying to enhance the efficiency, deliver more improved performance over silicon. There is also, even though the cost has come down for silicon tremendously, there is still a reasonable amount of embodied energy. And that's where some of these newer thin film material and technologies have also a role to play. What I'm going to do now is just dive straight into telling you about perovskites. So perovskite is, as a material, is calcium titanate. This is a mineral found in the ground. This is not what we use to make solar cells out of. This has this ABX3 crystal structure, but any material that adopts this same crystal structure is considered a perovskite, part of the perovskite family. It's related to the crystal structure rather than the elements that are within it. The materials that we found are excellent solar absorbers are predominantly based on lead halide perovskites, and these aren't new. These were around before a long time before the silicon solar cell hit the scene. First reported in 1892, but not much was done with them for a while. In the sort of early 90s to 2000s, there was some activity looking at similar materials, lead and tin halide perovskites for optoelectronic applications, transistors and light emission materials. But actually, the research was soon superseded by organic electronics that gained a lot of speed and a lot of excitement. And of course, that's led to the commercial OLED, but perovskites were forgotten about. And Richard Friend's obviously been seminal in the advancement of the organic electronics. Another key development in this field of perovskites was in 1978, when someone reported a hybrid material. So using an organic cation, an organic positive ion in the crystal, rather than cesium, the alkali metal material. At the time, it seemed like a curiosity. Now, it wasn't until 2009 that the first reports of use of perovskite in a solar cell were reported. And this was from a Japanese group led by Tom Miyasaka. They, at the time, were working on dye-sensitized solar cells. This was a novel type of solar technology that used a porous titania electrode. And on that porous titania, there were lots of dye molecules absorbed or stuck. The dye molecules absorbed sunlight, and then the excited electrons, after the absorption of light, transfer into this porous titania, and the conduction of electrons is through the titania. And what Tom Miyasaka and his postdoc Akira Kojima did was they took some solutions of the salts that make up perovskites and coated them into these porous films. And what formed were you can't see very well, I don't know how good your resolution on your screens are, but small little nanocrystals of these perovskite materials formed on the TiO2. And the film was thick enough that they could absorb sunlight, and they then filled this with an electrolyte, a liquid dye. And this resulted in solar cells that work. This is the spectral response. These are sort of percentage of photons converted to light. And the efficiency was around 3.5%. So they worked. One of the big challenges there was that the electrolyte dissolved the perovskite. So they literally lasted for tens of seconds. So this wasn't really followed. I started collaborating with Tom Miyasaka and also one of his colleagues in Toan University, Takeru Murakami, and we thought these perovskites looked quite interesting. So we wanted to look at them in our solar cells. We at the time were using this porous TiO2 electrode, but we were filling it with an organic hole conductor, a P-type, an organic semiconductor, which was solid, so it didn't dissolve the perovskites. And very quickly, we got efficiencies of sort of over 7%. And at the time, we were super excited about this because our lab record using dyes was 5%. So these were already quite a lot better. But what we observed doing some electronic measurements of these devices, we observed very fast current extraction. So the charge was seeming to conduct very quickly out of the cells when we used perovskite in comparison to using a dye. So we postulated that possibly we were having electron conduction through the perovskite phase as well as through the TiO2. So to test this, we replaced this porous electron transporting electrode with a porous insulator, alumina, and then constructed solar cells primarily to see if we had any electron conduction when we only had the perovskite that can conduct electricity. And absolutely surprisingly, the performance of these cells actually improved and they went up to over 10% efficiency. So this was our real first surprise breakthrough, was that we no longer needed this porous electron conductor to transport the charge. What we discovered was that if we controlled the processing, instead of processing nanocrystals, we could process smooth polycrystalline thin films. And this is a top view of an electron microscopy image. These blobs are they're crystallite grains, but they're on the sort of hundreds of nanometers to micron length scale. And this is a cross-sectional view of the thin film. And these thin films had remarkable optoelectronic properties, very long carrier lifetime. So the charges, when you photoexcite, if you pulse them with light, the charges live for a long time in the material before they recombine. This is unusual for a polycrystalline semiconductor. They had high luminescence efficiency. So when the charges recombine, a large fraction of them end up re-emitting light. And I'll come back onto this later, but this is an important property. It indicates very low defect density, low density of electronics defects. And in fact, this was something we did early on, collaborating with Richard Friend. We sandwiched one of these polycrystalline films within a cavity. And when we pulsed that, we could get lasing from the perovskite material. And usually to make a material that lasers, you've got to really control the defect density. The purity of the lead halide salts we were using were only 98%. Usually semiconductors require 5 nines or more in terms of purity, 99.999% purity. These didn't. They worked even with impure material. So this was part of the surprise. So that all mounted together to indicate that we could actually construct simple planar heterojunction solar cells. So instead of taking a porous scaffold or an insulating scaffold, we could actually just process a solid thin film of the perovskite absorber. Again, this is a cross-sectional electron microscope image. And then if we had selective contact on each side, this is a material, tin oxide, and an organic electron transport material. This will only allow electrons to flow in this direction, and then an organic hole conducting material only allows positive charge to flow in this direction. These solar cells worked very well. And in fact, this is the structure now that represents the record efficiency single junction cells that have risen to over 25. And I think people are even talking about 26% efficiency. Moving on from the first materials we looked at, and these were still basically methyl ammonium lead triiodide, we wanted to see what else could we make that could be useful. So the first material reported was this cesium lead triiodide. Methyl ammonium was reported in 1978. Cesium is actually a little bit small to stabilize the lead and the iodide in this perovskite lattice. Methyl ammonium's better, it's bigger. We can't use anything just from the periodic table. This now has to be a small molecule to be large enough to fit in this crystal. We actually found that formamidinium, a slightly larger organic ammonium salt, fits very well. At this time, this was 2012, 2013, that we discovered formamidinium lead iodide makes a good, stable perovskite compound. We thought there would be thousands of other elements and materials we could find. And in fact, there's quite a lot of effort trying to find new halide semiconductors. So far, in terms of a 3D perovskite, this is basically all that works. Also incorporating tin or germanium, bromine, chlorine, and chlorine. A key advancement that we made in stability actually related to this transition from methyl ammonium to formamidinium, and I'll just illustrate it here. But in fact, if we mix formamidinium with cesium, so we have the mixture of ions on the A side, this gave even further improvements, a better quality crystal, more crystalline, fewer defects, and really good thermal stability. And this is just an illustration of some photographs of films held at 130 degrees. If we use the methyl ammonium cation, they go yellow after about 6 hours. And that's because this smaller organic ammonium cation is more volatile, so it's driven out of the film, whereas the formamidinium containing, cesium containing material stays fully crystalline with no degradation. So this was a big step forward on stability. Another advancement on stability has come generically by adding additives. And I say that in a very broad sense. There's basically, because these materials can cope with impurities, they can also cope with a lot of different additives being added in. And we don't always understand what the additives do. This is an example of a piperidinium salt. It's a large organic ammonium, well, quaternary ammonium cation with a negative anion, BF4 minus negative anion. This reduces the defect density in the perovskite material, but massively improves the stability. This is some solar cells that aren't encapsulated, they're not laminated, they're just open at 60 degrees in air under full spectrum sunlight, and they're lasting for a few thousand hours before they've degraded below 80% of their initial performance, compared to the control that they degrade quickly. Now, this by no means suggests these are going to last for 25 years, this specific innovation, but it shows the sensitivity and the ability to suppress some of the photo-induced degradation processes by adding additives. So this is a big area of understanding, and there's probably 1,000 different additives the research community's tried to put into the perovskite. Some make it much, much worse, others cause improvements. I mentioned before these materials luminesced right from the start, and as processed, they're pretty emissive, but actually we still have losses and we still need to improve upon that. And one way we can improve upon that is by passivating the surface. This is a schematic illustration of the different materials in the device stack. The perovskite absorber sandwiched between a transparent conducting oxide and a metal contact with an electron transporter on one side, hole transporter on the other side. And then between the perovskite and the electron transporter, we've put a passivation layer. We've treated the surface with something that inhibits the defects. And that results in a big boost in open circuit voltage, going up from 1.2 to 1.35 volts. These materials are now so well passivated that even in the electronic devices, when we run them under forward bias, they actually operate as an LED. So this is the EQE as a function of voltage. And on the right, I'm showing you a video of us cycling a solar cell to forward bias and back again. So you absolutely cannot do this with silicon. You cannot get visible light emission of this sort of efficiency. This is about 3% efficiency. Actually, if you compare it to, for instance, an optimized LED device in a similar configuration, an OLED, this would be up at 20 to 30% efficiency. So it's not bad. It's not competitive. It's not an LED that you'd use in a display, but it certainly shows these materials can be very high quality. And in fact, as we progress towards further optimization and improvement, these devices will actually emit as efficiently as an LED. And that's one of the challenges going forward. The trick for high efficiency, and it's not something that's new for perovskites, but it's to move to multi-junction cells. We know the solar spectrum comes in many different colors. The blue end has high energy and the red end has lower energy, then further into the infrared. And the maximum voltage you can generate from a solar cell is lower, just a little bit lower than the band gap energy. And the band gap energy is the energy at which above the band gap you absorb photons. So silicon absorbs out to the infrared, but it can never generate more than about 0.75 volts open circuit voltage. Whereas if we stack different materials on top of each other, we can slice the solar spectrum up and generate higher voltage from the higher energy photons. In doing so, we improve the efficiency. So one of the obvious things to do is to match perovskites with silicon. And here, these solar cells have already, real solar cells have been measured at over 31% efficiency for perovskite on silicon, which is far beyond silicon on its own can ever get to. And we can even go further and go to an all thin film technology. And ultimately, this should lead to lower embodied energy. This is an example of a cross section of a triple junction cell where we've tuned the band gap of the perovskite to absorb in the wide band gap, mid band gap, and low band gap. And the highest efficiency of 28% has been reported, not by us, but by others, for a tandem cell, just two junctions on top of each other. But ultimately, efficiencies are approaching 40% could be achieved by these three junction devices. So for the last few slides, I'll talk about the industrial interest. I'll say a few more slides shortly about Oxford PV. That's the spin-out company that I started, but there's a lot of activity in perovskites. These are other startup or early stage companies working on not necessarily perovskite on silicon, but on thin film lightweight perovskites, flexible perovskites, rigid modules for thin film technologies. There's also existing electronic companies active in this area, and there's many more to come. Just as an illustration, there was a recent startup prize in the US that attracted something like 20 applicants of startups that I hadn't previously been aware of. So I think we're going to see more and more activity in this area because of the opportunity. And I'll just finish with a few slides telling you a little bit about our industrial journey. So I started Oxford PV actually in 2010. That was before we'd had the breakthrough in perovskites, but as soon as we had these breakthroughs in perovskites, we focused activity in the company entirely on perovskites. There's a facility in Yarnton in Oxfordshire, which is the headquarters and R&D facility, and we've got a production line in Brandenburg in Germany. So alongside the science and publications, we've also been filing a lot of patents. And this is to create the opportunity to have freedom to operate and also to give confidence to investors to put money in because they know that they're going to be able to capitalize on this technology when it's successful. This was an assessment done in 2018 by Syntelic, showing the sort of, we are highly active, but there's many other people also looking at pursuing lots of patents. And of course, we're trying to grow our patent portfolio to be as strong as possible and give us the prospect to deliver a technology that works and that can be sold. Oxford Photovoltaics is focused entirely on perovskite on silicon. So it's basically processing perovskite layers on top of standard silicon solar cells. We've chosen silicon heterojunction cells because they're very efficient. And then integrating them into what appears to all extents and purposes a standard PV module, apart from the fact it's producing more power. A lot of the work in the company has been improving the efficiency, starting from our first tandem cells of 21%, moving up to a series of world record efficiencies, getting over towards 30% efficiency. And then in the Brandenburg facility, it's about ramping up processing on large full-scale wafers to lead to wafers at 27% efficiency or thereabouts. And I think this is probably, this is a certified wafer at 26.8% efficiency. That's probably I'm almost certain that's the highest efficiency full wafer of this size of any PV technology ever made. Efficiency is one aspect, but stability is obviously critical. These modules have to last for 25 years. And a lot of the activity we've been doing is going through various degrees of torture for the solar cells. And this is following the IEC 61215, which is the industry standard test. But anyone in the industry knows that this is just a stage gate, and it doesn't guarantee by any means, not even for silicon, that the technology will last 25 years. Typically, the industry stressed to 3 or 5 times IEC. So that's what we've been doing. We've been looking at damp heat for multiple times IEC, multiple thermal cycles, light-induced and temperature-induced degradation under high light and temperature, on small cells and also full-size cells, and now on modules as well. So this will all culminate in our targeted module. I'd like to say you can buy this now, but you can't. But hopefully next year, these will start to be actual products where we're going to take our 27% manufactured cell and integrate it into a standard 60-cell module, which will start as the highest efficiency module on the market. But of course, this is just a starting point. The prospect for further improvements and further innovation, the headroom is massive. And over the next decade, this will move up to 40%, 30%, and then beyond. So with that, I'd like to just thank my research team and all my collaborators and Oxford PV as well. And thank you very much for your time. And I look forward to the discussion.
Thank you very much. Thank you very much, Professor Henry Snaith, for your presentation. I have to say that it's so informative and also a very easy to digest presentation even for people like me who have very limited insights and knowledge about solar energy and as well as perovskites. And we have to say that we are so lucky first to have our chair of the Prize Council, Professor Sir Richard Henry Friend. And then thanks to his connection, we have the chance to talk to and have the presentation from Professor Henry Snaith today in our webinar. And right now, I would love to introduce and invite Professor Henry Friend to have some reflection and discussion with Professor Henry Snaith about this presentation. Please, Professor.
So, Henry, thank you very much. That's a wonderful story. And what you gave us was a real how the story unfolded account. Very often, by the time something has been manufactured so that we can buy it in the shops, the actual story about what was done to drive up efficiency, to improve stability, is hidden behind all sorts of commercial confidentiality problems. So we never really know about the true story. But what you told us about was how very, very quickly all these difficult problems, which traditionally would take decades to solve, you managed to find very quick solutions to. And that sense of the rapid pace that something unexpected has been taken all the way forward to being ready to use was what I think is so powerful about that story. I can comment further that you underplay just how important it is to raise efficiency. Even a few % improvement in the efficiency of solar cells makes a huge difference to the economics for rolling out large solar farms. And it's absolutely critical we do that. If we can drive solar costs down a bit more, then solar will be completely the best solution for energy generation almost everywhere. So it's a wonderful science story, but its implication for getting to zero carbon is really important. So thank you for that.
Well, thank you, Richard. I must say, I mean, I've shown obviously some of the key developments that we've done in the research group here in terms of the technology. And I've had a number of people obviously working in the group, but we've also had a lot of activity in the company. And of course, what I haven't revealed is the precise composition and additives, if you like, or interface or materials that have been used in the commercial photovoltaic devices. And there's been, you know, more work done in the company to get from what looks very promising from the research groups to something that actually will make a product and stand the test of time. And this has been, you know, a lot of dedication of a lot of engineers and scientists on the commercial side as well.
So I mean, Henry, you're right to point that out, and it's very important that you that these are stories which are understood. I think too often the general public does not hear enough about what it takes to translate discovery through to a real product. And obviously you haven't revealed all the secrets, but you've given enough of the story to give that sense of how things really move in the real world. For me, I think it's very important that we all hear stories like that. It's inspiring, that sense that there is a lot of discovery still to happen, and that even quite small teams can make big changes. That for me is so important.
Thank you. I would just follow up on your comment about the photovoltaics as well. So I didn't labor on how wonderful solar is, but obviously I strongly believe that. And in fact, when we look at cost of power generation, there are solar, you know, with existing technology, existing silicon, the price purchase agreements getting pretty close to 1 US cents per kilowatt hour. Now, that's incredibly cheap and much cheaper than the hottest places in the world. But there's every prospect. I think the global average price for solar electricity is about 4 to 5 US cents per kilowatt hour. There's every prospect with improving efficiency and continued scaling that the price will get down to a global average of 1 US cent per kilowatt hour for the production of electricity. At that point, nothing can compete with it. Now, solar, we don't want to pretend, well, we could power our world entirely from solar if we had the storage capacity, but of course, wind and solar also complement each other very well. Often when it's stormy and windy, it's not very sunny. So the deployment of, I'm not suggesting that solar will be 100%, but it could certainly be a significant fraction and go for them from the 3.5% today, possibly even to as high as 70 or 80% power generation capacity from solar, with just 20 to 30% from wind would be my prediction. And I'd suggest that will happen or should happen by 2040. And actually, if you project the rate of progress of the industry and assume there's no technical or supply chain issues, then that should continue. And of course, what we're doing with perovskites gives a completely different supply chain for materials. And that does also, in principle, also reduce the embodied energy, the amount of energy input we need to put into manufacture. So this could cause or help to keep the acceleration rate going for the solar industry.
So I think we're starting to get some questions
coming in.
Can I perhaps turn to the MC to lead that?
Sure. Thank you, Professor Richard. And thank you for your reflection. I think that, of course, we are having a lot of questions. But first, I want to share with you that in the room today, in the meetings today, we have a lot of leading scientists and also very active scientists in this field in Vietnam also. And we have the scientists from Materials Research Society of Vietnam, and also from Vietnam Academy of Science and Technology, Vietnam National University in Hanoi and Ho Chi Chi Minh City, Hanoi University of Science and Technology. And we would like to say thank you so much for joining us in the webinar today. And we hope that your group and all of the scientists here will have great questions for our chair and also our speakers. The first question I would love to ask, maybe from Dr. Thuật Nguyễn, I can see in the meeting room right now, from Nano and Energy Center, Hanoi University of Science. Can you hear me, Dr. Thuật Nguyễn?
Yes, I hear you. So do you hear me?
Yeah, we can hear you well. So now you can share the question to our professor. Thank you.
Okay. Thank you very much for your presentation. I see that you have many breakthrough in perovskite solar cell, and I have to say that back in 2013, when I prepared a research proposal in perovskite solar cell, I read your paper, your Nature letter paper about the deposition, vapor deposition of silicon solar cell, planar perovskite solar cell, and it is excellent. So, but now when I see your presentation, I have a curious question about why the main reason why you spin off Oxford PV, but at that time in 2010 you do not have many breakthrough in perovskite solar cell. But what is the main reason to start this company?
Yeah, thank you for the question. Absolutely. So at the time I was working on solid state dye-sensitized solar cells. There was actually a lot of activity, commercial activity on electrolyte-based dye-sensitized solar cells. And I didn't see any future for a PV technology with electrolytes. So I had the presumption that I was actually working on the best technology and that no one was really trying to commercialize it because it was challenging. And I knew at the time I was going to spend a lot of effort improving this and finding out new ways to make them more efficient and more stable. So I thought there was a commercial opportunity. We'd filed 4 patents related to solid state dye cells at the time. And I decided that instead of trying to license those to an existing company, it would be better to try to raise some funds and try to push a startup company. It'd be a better way to have, in essence, some more control over how it's commercialized and also have that industrial direction to improving the technology. We were targeting semi-transparent PV for buildings at the time, so spent a lot of time discussing PV technology with architects. And after we first published our perovskites or discovered the perovskites were so efficient, we actually started for about a year trying to make semi-transparent perovskite PV, because at the time it was efficient, but we didn't think it wasn't anywhere near taking on silicon. So we were making actually perovskite PV for windows for buildings. And of course, there's still some companies trying to do this. But then when the efficiencies just kept rising and we realized we had really high voltages, and the high voltage is important for a wide bandgap material. There's very few materials that just absorb visible spectrum and give you a very high voltage. So we recognized very early on that meant we could use these in tandems and that we could use these on silicon. So at that point, which is about 2014, we shifted all effort in the company. We made a clear decision. We're going to abandon the thin film BIPV, building integrated photovoltaics product, and just put all efforts into beating silicon. And that was we had to be quite brave to do that because the present industry is obviously very well established. But what we've realized is by combining perovskites with silicon, we can actually work with the existing PV industry. So at least to a certain extent be seen as a benefit and an add-on and enabling silicon to actually advance to the next level.
Okay, thank you very much for your sharing. I see that you try many products in order to go to the final product at the present. Okay, thank you very much for your answer.
Thank you.
Thank you.
Thank you, Dr. Thuật Nguyen. And follow up on the question of Dr. Thuật Nguyen, I just want to have a very small question, not really scientific, but I'm just curious about the long time that you have been sticking with this field, and you try to figure out what's the problem, and then you try to take advantage, not only take advantage of the material, the perovskite, but also based on the characteristic of the lights, right? As in your presentation, I just want to ask, during those long time of developing and discovering perovskites and solar energy, what is the moment or the period of time, or what kind of achievement or realization that you feel proud of the most or remember the most?
Well, I think I presume my proudest moment is still yet to come, because it'll be when we have proper commercial product being deployed in the real world, and when we're actually generating power that's making a difference. If we've got this acceleration of deployed solar, if we can tip that curve to make that go faster and had an impact there, even if it's a small impact, it obviously has a potential to be a massive impact. But having an impact there, that'll be what I will have been proud about most, and that's yet to happen. On the development side, there's been a number of key moments in the scientific discovery, whether they're moments to be proud about or moments to just relish. You know, when we first observed that we didn't need this porous structure, we were completely set on the idea that we needed some mesostructure. We needed to take these easily processed materials and make them, in essence, nanoscopic, because we didn't imagine we'd get long-range carrier diffusion in a material that you could just solution process or vapor deposit at room temperature. So that actually, even though it now sort of seems logical with hindsight, it was actually had to completely switch our way of thinking upside down. And another aspect I'm proud of is the fact that I've trained lots of excellent scientists who've gone on to do some fantastic research in their own rights, and also get leading jobs in industry as well. So thank you.
Yeah, you are doing a lot of jobs right now. You are doing your research with your colleagues, and then you are trying to inspire and training a lot of other scientists for the future. And I'm just wondering how many hours a day for you to sleep?
Well, I think I'm quite good in that sense. So I think thinking time is really important as well. So it's not about the hours you spend in the day working, it's about the quality of those hours.
Yeah.
And in fact, to improve the quality, you do have to rest and take time out as well. So I'm certainly not working all hours of the day.
Yeah, I'm just joking about that. But actually, if you really love what you are working, it's not a work, it's not a job. It's just holiday day, right? And
Yeah.
we're getting back to today's webinar with a lot of questions waiting for you from our scientists. The next question from Dr. Lam Nguyen at the Faculty of Engineering, Physics and Nanotechnology, University of Engineering and Technology. Please, Doctor.
Yeah, thank you. Thank you for Professor. Can you hear me?
Yes. Yeah,
Yeah, we can hear you.
Okay, thank you. Okay, I'm very interested with your talk today, and I have some question about the tandem cell structure. Usually, we need to care about the current matching and also about lattice mismatch when we fabricate the solar cell structure. So, in your solar cell structure, in tandem solar cell structure between silicon and perovskite cell, how do you solve this problem?
Okay, so firstly, lattice mismatch. This is an issue with 3-5 semiconductors where they have to be completely crystalline. So things like gallium arsenide, grown by molecular beam epitaxy, has to be completely crystalline to be of high quality. If there's defects in there, it causes problems. So because of that, those materials need to have their lattice matching with the layer upon which they're grown. Actually, perovskites, this is a key difference of perovskites, is they're polycrystalline materials. So they have a crystalline surface, but that just forms, they don't have to match with the underlying interface. And in fact, often we have them grown on organic semiconductors where there's no ionicity in the organics. It's just covalent carbon bonds, if you like. And there we don't have lattice matching. So lattice matching isn't an issue. In fact, there's organic molecules, especially for the hybrid perovskites, the organic ions will go to that interface and they'll help to passivate defects that would otherwise occur. But we don't need to worry about lattice matching. We can have multiple polycrystalline layers that don't have lattice matching. As for tuning the band gap, we can tune the band gap. We've got the sort of family of ions that we can form composites with, and actually just mixing in a certain fraction of bromide with iodide can get us to the right band gap. So we absorb precisely half the light that the silicon cell would have absorbed. And in doing so, we absorb all the visible light. So let's, just as an illustration, if the silicon solar cell would generate 40 milliamps of current density, it's absorbing certain fraction of the sunlight, 2/3 of the solar photons. We want to generate 20 milliamps in the perovskite cell. So we just want to absorb the top third of the solar photons. So the middle third go through to the silicon cell, and that gives us our current matching. Now, the solar spectrum is never the standard AM 1.5, AMS 1.5 that we optimize the cells to. So in reality, they're always they're always slightly mismatched, but that doesn't matter, because actually when you generate more current, a bit more current on one of the junctions, it pushes that junction towards open circuit voltage. So what that means is that your operating voltage actually shifts out a little bit, and this compensates a bit of a drop in current. So your efficiency actually does not change very much when you mismatch by plus or minus 10%. So there's quite a lot of tolerance there.
Yeah, thank you, Professor. And I have one small question. When I see the presentation, I see you use the black reflector for deflect anti-deflection, black reflector.
So the commercial perovskite on silicon modules will be bifacial. They'll allow light through from both sides, because even though that causes, in essence, that means you've got to change your band gap of your top cell a little bit, because you're getting more light to the silicon. So it changes the current matching requirements, but overall you get a boost in performance. So we may as well do that because we're using heterojunction cells that are already bifacial on the silicon side. In terms of the anti-reflection, actually in a commercial module, again, the lamination foil has its own anti-reflective properties when laminated on top of the wafer. So you don't actually need an extra anti-reflective layer. That foil's designed very well to couple light through glass into the foil and through into silicon. That's a very high refractive index material. In fact, the perovskite cell on top of the silicon acts in part as an anti-reflective layer for that infrared light as well.
Yeah. Yeah, thank you very much, Professor.
Thank you.
Thank you for the talk.
Thank you, Dr. Lam Nguyen. And right now we have a question from a doctor, a scientist who is in this meeting room, and he's raising his hand right now. Dr. Viet Tung, can you hear us? Can you turn on your mic and send the question to our speaker? Dr. Viet Tung, can you hear us? Okay, so we'll come back to Dr. Viet Tung a little bit later. And now we have Dr. Trường Liên. Also, he's also raising his hand right now.
Okay.
Are you here?
Okay, firstly, I would like to thank your
I'm sorry. Yeah, you are female. I'm sorry. We have a female scientist.
No problem.
And please introduce about yourself first, and then send the question to our speaker. Thank you very much, Dr. Chim.
Firstly, I would like to say that I'm a physicist and I like physics very much. However, at the moment, my research is not focused to the solar cell. However, I have two questions. The first one is, as you said, one of the great advantages perovskite offers is the great tolerance of the defect in the structure. Unlike silicon, extremely high, which require extremely high purity to the function well in electronic device, but perovskite can function well even with numerous imperfection and impurity. And I know that the perovskite refers not to a specific materials, like but to a whole family of compounds. Then my first question is, why do you think perovskite could take solar cell to new height? And the second question, when I saw in the structure, they need been using lead materials. This, I think, the impact to environment. Yeah, and do you have any thing or the plan to avoid or to eliminate the use of lead in the future? Thank you very much.
Thank you very much. Two very good questions. So I'll start with the first one, which, if I interpret it correctly, you're asking me, why do perovskites work so well? Why do they work when they're impure? I mean, this is almost like the ultimate question, because once we know that, hopefully we can discover other materials that also work as well. So my sense and the general feeling is it's to do with two factors. One is that most of the bonding is ionic in these materials. And there's been theories from a long time ago. And if you look at the sort of defects that will emerge when you've got ionic bonding, the energy of those defects is more likely to be near the bands, the continuum of states, than right in the middle of the band gap. Whereas, for instance, in silicon, when you have a dangling bond, the energy of that defect is right in the middle of the band gap. So it acts as a strong charge trap. So the defects that form, that we have many defects in the perovskites, they probably lead to energetics that are near the band edges. And there's been lots of theoretical calculation of the position of these defect levels, which, and of course, they don't all agree with each other, so we don't know what the absolute truth is, but they certainly seem to be close to the band edges. So that's one reason. The other, and it's something I didn't mention at all, it's a consequence of the ionicity of these materials, is we have actually quite a lot of ionic defects that are mobile, and lots of mobile ionic species. And there you can imagine that these ions will drift and accumulate around the buildup of charge. So it may well be that the trap charge, if there is trap charge that exists, that it gets stabilized by some ionic species in its close proximity, so basically taken out of the game. So that ionic nature and the ability for the ions to move around could also be part of the reason why they work so well. We don't know that yet. We know there's problems that the ions cause. We essentially predominantly want to reduce the ionic diffusivity, and especially for long-term stability, but there could also be some advantages. Now, on to your final question, or your second question about lead. So lead, absolutely, lead is a toxic material. You would not want to ingest it. But especially for photovoltaics, you have to look at the whole life cycle analysis, the whole life cycle environmental impact, including toxicological and all other metrics, to understand whether lead is bad to be in the module or not. And we've been involved in a lot of European consortium where we've done these sort of analyses. And the short answer is that lead has a minimal negative environmental impact, both on human toxicologically and on water ecotoxicity. The availability of lead, it's massively abundant. Today, we use a lot of lead. And I could give you a lot of statistics, but one that I'll just state is that if we wanted to produce 12 terawatts of perovskite PV, which is more solar than we need to power the world, if you amortize it over 25 years of production, we'd only need about 1 day's worth of today's annual lead supply. So we're not going to be introducing much more lead into the environment. On top of that, we've done other studies where we've been looking at the sequestration of lead into soil, actually taking real soil samples and seeing what is the environmental fate of lead. And actually, it's very rapidly, within a few hours, taken out of the aqueous phase and absorbed into the lead, where chemistry happens and the lead becomes immobilized. So it's locked in the soil. In the worst case scenarios where all the lead leaches into the soil, if that were to happen, we'd still have lower lead content than, there'd be a low enough lead content, certainly in Europe, then you'd have to take action to perform any remedial activity. And in fact, it would be, you'd be able to farm on that land even if you leaked all the lead into the ground. It would be below the content where you can no longer produce food on the land. Now, I'm not saying we want that to happen. We've also done studies where we've taken modules, completely smashed them up and left them outside for 9 months. And this is quite a surprise even for me. The modules completely bleached. The perovskite clearly became hydrated, but only about 1% of the lead that was in the module leached out over 9 months. So even if they crack, it's not that all the lead's going to rapidly leach out. And this was without having to put in any special, these were normal lamination foils and edge sealing, normal glass lamination. We're not using any fancy getters or something to specifically capture the lead. So I won't labor the point anymore, but it is a really important point. Of course, it's easy to assume that lead would be bad, and of course we're restricting it in electronic goods, but actually the positive impact of perovskites, and if we do a full environmental life cycle analysis on a perovskite on silicon tandem that we've done, about 40% of the ecotoxicity impact comes from the silicon, about 30% from the indium in ITO, if we use ITO. And assuming all the lead is emitted into the environment, which will not happen because they will be recycled, but if we assumed it was all limited into the environment, only 0.3% comes from the lead. So, and then if you say only 1% of it could ever leach into the environment, then you're down in you're in the noise of the impact. So the truth is that lead should not be a problem. And actually, as scientists, we need to make sure that we perform all the correct studies and verify that, and then do our job to make sure that legislation doesn't get put in place which would stand in the way of this very important progress. The benefits of simply raising silicon module efficiency by 20% would have so many positive environmental impacts that we need to make sure that it doesn't become legislated against, and that becomes the biggest barrier, potentially a barrier to this green technology. And then just very quickly, yes, we are looking at other materials, but not because we think there's a problem with lead, but because we think there's new opportunities for new materials.
Okay. Thank you very much.
Thank you, Dr. Trường Liên, and thank you for your question. We would like to share that in Vietnam now, this topic of solar cell is getting more developing, and it's draw lots of attention from the science community. So today, a lot of Vietnamese scientists are here, and they are very exciting in getting more questions and sending more questions to you, Professor Henry Snaith. And the next question will come from Dr. Nguyễn Quang Liêm, as I can see in this meeting room. Can you hear us, Dr. Quang Liêm? Hello, Dr. Quang Liêm. Can you introduce about yourself and then send the questions to our guest speaker?
Okay, thank you. Can you hear me?
Yes.
Yeah, we can hear you. Keep going,
Good.
Please.
Yeah, my name is Nguyễn Quang Liêm. I'm working in the Institute of Material Science, Vietnam Chemical Science Technology, and my major is solid-state physics, and work with the optical characterization on the semiconductor. Yeah, thank you, Snaith. It's a very nice talk, very informative, and a nice discussion. I have one question, two questions, but one is very basic. You use the perovskite, and you see this good luminescence materials, meaning that if you generate electron hole, the recombination rate is rather high. So this is something is not very good for solar cell, because when you generate an electron hole, it should be very quickly separated to the electrode to get energy. So what is the problem or the essential behind this phenomenon?
Okay, so thank you for this question. It gives me an opportunity to explain the light emission of a solar cell and why we like light emission from a solar cell at open circuit. So under operating conditions, the current is being extracted to the electrodes, and you want to get the charge out. So under operating conditions, the solar cell doesn't emit light, or not very much light. And especially if you're at short circuit in the solar cell, any light emission at short circuit indicates that you haven't extracted your carriers. At open circuit, there's no carriers being extracted, or at least the carriers being extracted are matched by carriers being re-injected. And the fact that it's emissive means that the only recombination events that are taking place are the band-to-band recombination, conduction band electrons recombining with holes in the valence band. That doesn't have to be a fast process. It's reasonably fast in perovskites, but that is because the materials interact with light so strongly. It's a consequence of their very strong absorption spectrum. There's a reciprocity between absorption and emission, and it's fundamental. If you have a high absorption coefficient, you've got a high emission coefficient, but it's fast on the multiple tens of microseconds timescale, not on the nanosecond timescale. What you're really referring to for LEDs is where, certainly for high efficiency gallium nitride LEDs, quantum wells are used, and this confines the electrons and holes, so they do recombine fast in those structures, and they recombine fast so that other non-radiative recombination events don't happen. It makes it much more competitive for light emission than trapping and non-radiative recombination. But if you can engineer your solid non-confined semiconductor to have such low defect density that you get very high emission even when you've got unconfined electrons and holes, then that's the sort of perfect situation for a solar cell. So it is consistent. It actually indicates that even without confinement, we get very high emission. And I didn't mention in the talk, but there is a lot of work on perovskite LEDs, and a lot of that work boosts the emission even further by confining, mixing in larger organic ammonium cations that can't go into a 3D perovskite, so that you have domains or layers of 2D perovskite or domains of small little perovskite crystals within a matrix. And there you can get even higher luminescence efficiency in thin films approaching unity, approaching 100% emission efficiency. And in the LED devices, they're certainly over 20 to 25% efficiency. So but they're engineered to be an LED and a light emitting device. This is a solar cell that, as a consequence of the low defect density and passivation, operates also as an LED.
So it means you can benefit from the high absorption rate.
Yes, yes.
But don't suffer from the recombination rate, because you said that the decay times are rather long. And yes, you don't need to have any approach or engineering to separate, to promote the separation of the charge carrier. You don't need to do anything.
No, so it's I guess you could consider it a Goldilocks zone. The exciton binding energy in these materials is somewhere between 10 and 30 millieV at room temperature. That gives us quite a lot of increased absorption strength near the band edge, but it's low enough that 95%, the sort of equilibrium of excitons to free charge is 95% free carriers. So we benefit from much stronger absorption, which means in half a micron thick film, we can absorb almost panchromatically to the band edge, but we still have predominantly free carriers. So that's also a special scenario for these materials.
Okay. So my second question is that you have the tandem structure. So in my view, if you have different kind of materials and layer by layer or by any kind of deposition, usually it exists some energy there. That means some tensile or stress, something like that. So it will make the stability in operation in the future. So is it true, or you have to reduce it?
You have to overcome these things. So the perovskite absorbers themselves, they're the thickest layer they're very soft materials, so they can cope with quite a bit of strain. And in fact, as they crystallize, the strain will be released in them. There's not lattice matching with the layers underneath. We absolutely have to be concerned about adhesion between each layers. Otherwise, you can get delamination. And I mean, this has been a big activity. There's very, very little published in the research community about this, actually, but it's certainly been an important activity to get towards a commercial product to make sure that the adhesion between each layers is good enough. This is tested in two ways in the standard tests. One is thermal cycling, but it only is really revealed in modules or large cells rather than small cells where you've got big layers that can expand and contract. And the other is the bend test, where you put pressure on the modules and see that they're bending. Those are the two tests that can reveal delamination issues if you haven't got appropriate adhesion between the layers.
But you have any kind of accelerated test for lifetime of such kind of tandem solar cell?
Yes, so I mean, there's all the IEC tests, which are standard. They've been devised to reveal most of, if not all, the failures that happen in silicon. So the perovskite cells have to pass them. And then there's other tests that I won't say what they are, but there's certainly proprietary tests from Oxford PV to stress the devices and modules in different ways that aren't interrogated in the IEC.
Okay, thank you. That's clear. Thank you.
Thank you. Thank you.
Thank you, Professor Quang Liêm from the Vietnam Academy of Science and Technology, and all the scientist team from this academy. And the next question, we have one question for exclusively for our chair of today's webinar, Professor Richard Henry Friend. And the question will come from Dr. Trương Quang Trung. Dr. Trương Quang Trung, can you hear us? And can you turn on your microphone?
Hello. Thank you for the amazing presentation. I just initially want to have a question on environment concern of the lead perovskite solar cell, but you talked a moment before about that problem already. So for long-term stability of perovskite solar cell, is there any interest in using graphene material or CVD graphene for some conductive electrode or barrier film for solar cell application in your study?
I think that is a technical question that really should go to Professor Snaith. I mean, the comment, I briefly say that the challenge of encapsulation is complex. There are many elements to it, but the various layers within the device, the most important design consideration is to avoid light being absorbed, and actually graphitic materials are not brilliant because they're black, and we really want to make sure that no photons get absorbed to generate heat. But Professor Snaith, I'm sure, well, he's touched on it already, but I think there are just many elements to the overall encapsulation.
Okay, interesting. Thank you. Yeah.
So should I respond to that as well or not? Okay. Okay,
yeah, we are
okay. So I mean, as Richard pointed out, you probably wouldn't want to use something like graphene as the electrode, because to get the high level of transmission and appropriate conductivity, the 2D layer interacts too strongly with light. In terms of passivation, there's been a number of reports in the literature by others of using graphene or boron nitride, single layer boron nitride, to in principle encapsulate the perovskite cell on the perovskite cell. This is to inhibit the halide loss. So part of the photo-induced degradation is generation of halide, could be I2. This is a gas, and this will come out of the perovskite film. If it's held in, when the light is switched off, the perovskite reforms. So actually it's sort of self-repairing, if you like. If you don't lose the components, then you won't get very much degradation. And it also, just because of the, I guess, the surface pressure, if you like, of halide when it's trapped in the film, will just slow the loss, push the reaction back towards the perovskite. So certainly there's prospects there for lots of materials, and looking at materials that can both be very good in cell encapsulation and also charge transporters is certainly an interesting area. This is one of the areas where there may be future innovations. Thank you.
For the answer from Professor Henry Snaith, and thank you for the question from Dr. Cheung. And getting back to Professor Richard Henry Friend, actually, I'm so happy to see you being back with us in an activity. I can't help having a question for you. My question is that looking at what we are having right now in this field of solar cells and also the solar energy, and what rising star as Professor Henry Snaith are doing in this field, where do you think we are at in this field in the world, and what is the most important mission that we're having to do in the next phase or in the near future?
Well, I think what is so exciting and as beautifully shown by the perovskite field is that we used to just make solar cells from silicon because we could borrow silicon generated for other purposes. And there was very little fundamental research around solar cells. But now we know that we absolutely need solar cells. Solar energy is essential to decarbonize energy. So now it's become a really big field, and lots of people are trying new ideas out. Most of them won't work, but occasionally something does work. So I think we're in an era of discovery. We will carry on using silicon, but we will discover more things beyond the perovskites. I mean, the perovskites are almost certainly going to play a huge role, but now we are giving the same attention to looking for materials to work just as solar cells, new materials, and new device architectures. And I think that's very exciting. I think the opportunity that science will produce surprises is absolutely there.
Thank you, Professor. I think that what we have done, all the scientists have done in science to give the solutions to this field is like a fairy tale, because we have turned solar energy. It used to be a very, very expensive source of energy, but now we are making it affordable and scalable for a lot of people out there around the world. And we really hope, it's really hopeful that we will have this kind of energy being used by all people around the world, right? And to make a positive change for our world, like the mission and the vision of VinFuture Foundation, as we always say to our audience. And I know that on the way to advance the material and also to advance the solar cells, you have had a lot of contribution. So we really want to ask, do you have any updates or any new things to share with us about what you are doing, or anything new that you want to share with all of our audience?
What I'm doing? Well, Henry Snaith did mention organic semiconductors, which at the moment are a very, very important technology for displays, for OLED displays. And actually, there's some very big surprises in how they can be used for solar cells. The efficiencies have been getting a lot better. And they're now up to about 20%. It's not as good as the perovskites, but they've got better very quickly. And there's a parallel story that it would take too long to talk about it. But it's always the surprises that we don't expect. It's always possible to produce a list of reasons why something is not going to work. And quite often, those reasons turn out not to be there. So there's a particular problem about luminescence yield, which Henry Snaith talked about for the perovskites. And in the case of the organics, it's something to do, the particular culprit is something we call a spin triplet exciton. It's a dark, low energy state, which is formed as a recombination when electron hole come back together. And we've been investigating how to avoid that being formed, and then we can push up the efficiency of the organic solar cell. We're not nearly as far towards commercializing. At the moment, it's still in the realm of some fairly fundamental science questions, but it's that same sort of spirit of there being surprises that I think is an important takeaway message. This is, we're in the discovery phase.
Thank you very much, Professor. And before we finish today's webinar, we still have one more question, the last question from a very passionate scientist from Vietnam. Again, Dr. Thuật Nguyen. He's still have another question, the last question for all of you. Please, Dr. Thuật Nguyen.
Okay, thank you very much. Well, I have a question, but it's a little bit off topic of solar cell, but still we keep on the organohalide perovskite material because it is an excellent material for device, auto-electronic device. But my question is, when we go low dimensional, for example, 2 dimension, 1 dimension, then you have new properties of this material, such as high binding energy, exciton binding energy, and it even higher than room temperature fluctuation energy, thermal fluctuation energy. So do you think that we have any chance to have a kind of new device for new technology such as quantum and neuromorphic computing technology? How do you think about that?
So my short answer is yes, I'm sure there's lots of new opportunity. People are looking at different applications. They're looking at the effect of spin, whether these materials can be used to control spin or spin injection or spin transport. But it's very far away from my direct field of research, other than we are making layered 2D perovskites and we're looking at their interesting properties. Another aspect with these materials is you can dope them with elements as well very easily, and those elements can have different functionality, which I mean, in some instances been reports of multiple photon generation through a process called quantum cutting, where I'm doping with ytterbium as a rare earth that can result in 2 photons being emitted for every single photon, but also in terms of controlling spin, if we can put ions in that have strong spin and that can be controlled with a magnetic field in terms of the direction, this is something where there could be lots of prospects. Richard might have thought more deeply about these alternative applications than me, though.
Well, I think the spin is very interesting. And as soon as we have bound excitons, there are actually options to create quite exotic spin states with excitons. That's true with organics, it's true with inorganics. But I think that the general comment is that with the perovskites, the fact that you can tune color so easily, both by chemical selection, but also by the thickness of 2D layers, is really, really important. These are remarkably engineerable materials. It is possible to tune, as Henry Snaith has showed us, to get the right color for solar cells. But your question about going to 2D to look at excitons is a really good question.
Okay, thank you very much. It gives me hope because we now begin to dope, instead of iron, we dope mangan into the 2D perovskite so that we can have some combining effect between exciton and spin. So I hope that we have something new. Thank you very much for your
illustration. Yes.
Thank you.
Thank you, Dr. Thuật Nguyen, and thank you for the answer from our 2 professors. We have already had almost 2 hours together, but it feels like it's just like 20 minutes or like I think that still we have still a lot of questions from our scientists in the meeting room, but we cannot have more questions to send to our speaker in chairs right now because our time is up. And to end up the Q&A session, I just want to tell all of our audience, if you still have questions, please send the question to our email and send to the VinFuture Foundation, and we will try to contact our speaker in chair to figure that those question out. And for the last minutes of our webinar, we just really want to hear the feeling and some thoughts from our speaker, Professor Henry Snaith.
Well, thank you very much. Firstly, for all the great questions and asking me here to share this with you. Clearly, there's a lot of enthusiasm within the Vietnam community, the research community, for solar and for perovskite, and it's really, really great to see. I think the prospects for future advancements are massive. We certainly, within the realms of what we're trying to do at present with the multi-junction cells, we can see a clear pathway to 40% efficiency. I was obviously quoted in that video of saying that we could get up to much higher than that. I think the practicality of going beyond 3 junctions, possibly 4, is feasible. But then beyond that, I think we need to think of other means. So other ways, more advanced ways in which we can generate higher efficiency. And of course, that there may be concepts that we haven't thought of. I'm sure there are concepts that we haven't thought of that might be more practical than some of the other concepts that we have thought of, such as hot carrier collection. But possibly some of these slightly more wacky concepts might work if someone has a surprise discovery or there's a surprise material that does something unexpected. And of course, there are practical, I think the photon management, down conversion, photon multiplication, up conversion are real effects that work, and trying to integrate them into devices, maybe in combination with multi-junction cells, could lead to further steps forward. So prospects over the next few decades, I would say, for improvement are massive. And the opportunity for new materials discovery is also very vast. And I think what we'll see here, unlike silicon, where all the learning from the electronics field, optoelectronics was transferred to solar cells, what we're seeing in research, and I hope what we'll see commercially, is there'll be a lot of learning in solar technologies with perovskites that will then be transferred across to multiple other applications, maybe even spintronics. Thank you.
Professor, and thank you, Professor Sir Richard Henry Friend and Professor Henry Snaith, for attending us today. For your presentation, it's very insightful and also very meaningful sharings from both of you. And I believe and hope that after this webinar, our audience has gained a lot of things, and they have understand more about the situation and also about the development and discovery and the challenges in advancing the perovskite solar cells, and also about the acceleration of the solar deployment in the future around the world. And right now, I would love to invite all of you, all of the audience and our chair and our speaker, to turn on the to turn on the video, the camera, so we can see you and we can take a group photo, so we can remember the webinar today. After that, we can share the photo with all of you, so that we can have very memorable moments together. Please turn on your camera and we can have the group photo together. Yeah, we are now having a lot of people in this meeting room. We have Dr. Việt Văn Phạm, Trần Quang Huy, Cần Thu Vân. We have Hoa Nguyễn. Yeah, please turn on your camera. We are so grateful to have all of you, because we have prepared for this webinar for so long, and we hope that today we have given you a very meaningful and insightful presentation, as well as a webinar with a Q&A session. And now I think that we are all ready for the group photo. So please, I will count from 1, 2, 3, and smile. Another photo. 1, 2, 3, smile. Thank you very much. Thank you for being with us today. And last thing I want to share with you that please share all your experience, your opinion, and your initiative to the topic to our email office at vinfutureprize.org, and also help us to improve the webinar. Please send fill the online survey that we have just sent the link into the chat box. Thank you very much. Thank you, audience. Thank you, Chair. And thank you, our distinguished speaker. Thank you for today, and see you very soon. Goodbye.
Thank you. Bye-bye.
Thank you very much. Goodbye, all.